Okay, well, hello, good afternoon and welcome. So my name is Jim Pascoe. Today I'm going to talk to you about stack traces and in particular stack traces in C++. So I'm going to focus mainly on C++23 and the new stack trace library and how you can use it in interesting ways. But I'm also going to discuss some complementary libraries that you may not be aware of. So there are kind of two goals from my talk. Firstly, to show how stack traces can be used for more than just kind of debugging sort of logical errors. And secondly, to share some libraries and insights I found useful. So you can see on the slide my email address, my URL, if you want to find out a bit more about what I do. Also, the slides are online at the github.io URL. So if you're at the back and you think it might be easier to see, then please do follow along there. All of the code from today's examples as well is also on GitHub. So that's wrapped up with some CMake to make the build process a bit easier. Okay, so stack traces, traceback, call sequences. C++ calls them stack traces, as does C# and Python. They're called tracebacks. But I think we probably all recognize a stack trace as being a snapshot. So a snapshot of a sequence of function calls that have led to some interesting event. So typically an exception or an assertion firing. Primary use case, I'm sure that we've all used them for, is debugging logical errors. So for example, tracebacks in Python, which show you, if I call A, then B, then C, and something goes wrong in D, then I can ripple back up through the flow and see exactly what the events were which led to that. In the field, however, the nice thing about stack traces and how they enrich our debugging is that we can locate problems without a debugger. So that's quite useful. There have been times when I've been sat on trains with deeply embedded systems and actually just printing out a stack trace rather than getting a one-line assertion or an exception or a print that tells me I've hit some unreachable code. Actually getting a stack trace is really quite useful. Helps you drill into the problem a lot faster. And if you're under pressure, it can be, it can make a massive difference. Stack traces also very useful for introspection. So you can do things like look at object lifetimes. So one kind of common pattern, so something I do a lot with networking code, is to use RAII to manage the lifetime of things like sockets, buffers, that kind of thing, particularly if you're doing a lot of asynchrony as well. So you've got a lot of nested asynchronous calls. Then actually using RAII to manage those resources is quite a nice way of doing it. Stack traces is also quite useful with coroutines. So don't confuse the whole stack list versus stack for. What stack traces are doing is allowing you to look at the call stack, which is, obviously in the context of coroutines, has some quite interesting manipulations as well. The other thing which stack traces are useful for, signal tracing. So for example, I see this on Stack Overflow an awful lot. I've hit a seg fault in my code. I want to get a stack trace. Can I just print a stack trace from my signal handler? Well, the answer is sort of, but just be very cautious in this area because, as we'll touch on in the talk, the whole kind of signal safety, it's, there's some complexity, there's some subtlety there. So, stack traces in C++. All right, so before C++23, there was no standard way of getting a stack trace in C++. So if you wanted to get the current call stack, you had to use a combination of kind of compiler support libraries. It was possible, but it was a lot tricky. Now we've got, in C++23, we've got standardized stack traces, which is brilliant. This is really useful, and thank you very much to the people that did it. The proposal is this one, P0881. It's actually quite readable. It's only about 7 or 8 pages long, and it goes into some interesting details about why the library is built the way it is. Also touches on signal safety as well, which is quite interesting. So I'd recommend, sort of at least skimming that. There's not a great deal of standardese in it, so it's definitely worth a look. So I mentioned some complementary libraries as well. So one that I'm quite excited about, I find quite interesting, is CPP Trace. So this has been developed by a person called Jeremy Rifkin. It has a good treatment of signal safety. It's also C++11 compatible. So if you're, if like me in your company, you're thinking, well, I'd really like to use C++23 stack trace, but my company is still working with C++14, 17, have a look at CPP Trace. Also has a very good sort of coverage of debug libraries as well, so it's not just Dwarf. So definitely want to, sort of make a mental note, and I would definitely suggest having a look at that. Another interesting library as well is backwards CPP. This focuses on stack trace pretty printing, which sounds, a bit, why would you want to pretty print a stack trace? But actually, what you find is that when you start using stack traces in quite complex systems, is that actually the stack traces you get out can be themselves quite complicated. So having some view on, how you're going to print stack traces is actually quite important as well. So particularly if you think about, functions that have lots of template arguments and lots of parameters that each themselves have lots of template arguments, then it can get complicated quite quickly. The other one, which obviously is worth mentioning, is Boost Stack Trace, which is kind of like the mature gold standard, if you like. Or that also has a very good treatment of signal safety as well. So if you're interested in how you write signal safe stack tracing and how to do that, definitely worth having a look at Boost Stack Trace. It's what C++23 Std Stack Trace was built on. So definitely worth having a look at Boost Stack Trace as well. Okay. So let's see some examples. All right, so what I've got here is Fibonacci. So everybody understands Fibonacci. So this is my fib function. And what I've done basically is I've put in this class the ability to look at the stack trace as I go along, calculating Fibonacci numbers, and then cache the stack trace that has the greatest depth. And then what I'm going to do is I'm going to retrieve that and I'm going to inspect it. So you can see what I'm doing here is I'm calling this line in particular, so std stack trace. Actually, interestingly, if you just call std stack trace open paren, close paren, what you will get is a default initialized container, an iterable container of stack trace entry, which will be empty at this point. So you have to actually call this static method current in order to populate it with the current stack trace. So that's what that's doing. If we look at so obviously we've got a getter, and then if I look at how I'm calling it, I'm saying just calculate for me the first 10 Fibonacci numbers like this. I'm going to print out I'm going to get my maximum stack trace. I'm going to print out a maximum stack depth, and then I'm going to iterate through each stack trace entry, and I'm going to print out the source file, source line, and also the description. And the description is the name of the function and its parameters. So, simple stuff. Compilation and leaking. Okay, so I've been using GCC 13.0. If you use GCC, you need to enable your GCC build with this. So enable libstd cxx backtrace equals yes. I think just before I came to the conference, I think I saw a patch go in from Jonathan Wakely that actually turns this on by default. So I think from GCC 13.3 onwards, you won't actually need to do this, which will help quite a lot, I think, because a lot of default build. I mean, this is actually a C++23 feature, so you want it really to be just present. If it's not built, then obviously you can't use it. Now, interestingly, libstd cxx backtrace. Okay, this is the kind of the implementation. If you're interested in how std stack trace is implemented, have a look in the GCC trunk at these two files. So this is the include path to the header that we include in our user code, and also libbacktrace, which is a GCC library that implements the backtrace logic. So the way it kind of works is you have the std stack trace header in that directory, which is what you include in your code, and that's what you see on cpp-ref, and then that wraps libbacktrace, which is actually providing the underlying implementation. So yes, compiler options, obviously you need to say -g to give you debug, but also libstd C++ libbacktrace, and that is libbacktrace, not libstacktrace. Okay, as a, spent, sort of, you sit there thinking, why is this not compiling? And then you realize it's libbacktrace and not stacktrace. Okay, so the output. So we run our program, we get this. We get our prints. So first 10 Fibonacci numbers tells me that the maximum stack depth was 13. Okay, and then if I go from bottom up, so on line 14 you can see _start, which is the entry point to the process. So it's interesting what Roger was talking about yesterday with the ODR and stuff. We were talking about underscore start. And then on line 13, the next stack frame, next stack trace entry is actually in libc start main. Now, I've added this commentary just because I think it's quite interesting, it's useful. So a lot of the examples you'll just see 3 kind of colon zeros at the bottom. But if you, I'm using glibc on my system. So if you use GDB and you step through this code, what you'll find is that actually is quite a nice way of examining the C startup code. So if you want to actually have a look at how you get to main, it's quite an interesting way of doing it. Then we get to main, obviously, and then we've got a whole bunch of recursive calls to fib. And then on line 17, this is actually the point at which we called stood stack trace current. So that's obviously at the top of the stack. Okay, some observations. So the first thing you think when you see that output is, actually, I'd really quite like to be able to attach further information to stack frames. And you can do that because stack trace entry and, in fact, stood stack trace both have template specializations for stood hash, which is great. So you can use them with things like unordered maps. And then when you're going through your stack trace entries, when you're iterating through them, you can look up into a map or something or some other hash table and use that to index into some further information that you've cached. I quite like GDB for exploring this type of code. If any of you guys are using GDB in a sort of similar way, have a look at Andrea Kardash's GDB dashboard. So I've got a little screenshot of this coming up, but this is actually really, really good. If you use GDB on the command line, if you pick up Andrea's dashboard, it's just literally, it's a wget command, and what it does is it basically gives you a GDB init, which you put in your home directory, and then it just all works. So it's really quite nice. And the other thing, which I think is not kind of widely publicized about stood stack trace, is that actually there's an observer. So there's a function buried within stood stack trace that will give you a native handle. And what this means is actually you can go kind of one level beneath stood stack trace. So you can actually go into the realms of lib backtrace and pull out the underlying data structure that's in lib backtrace. So like I said, this is the dashboard that I was pointing out. It's very easy to install. If you use GDB on the command line, it's really worth just using this because you get this kind of really nice sort of representation of the machine, so it makes it quite a lot easier to work through. And you can see here that if you point it at glibc, you can go through that C startup code, which is actually quite interesting, quite useful. Okay, right. Let's have a more complex example. This is a web server. It's implemented using coroutines. So it's based on Boost Beast, which is an excellent header-only library that's built on kind of the ASIO primitives as well. So for those of you that have used Boost ASIO, what Beast gives you is sort of low-level networking primitives, HTTP support, and WebSockets. So like I said, it works very well with Boost ASIO. So if you come from that kind of mindset, it's quite a nice thing to pick up. And you can use it to develop little servers and explore things like coroutines and asynchrony quite easily. All right, so let's go through this quickly. Okay, so here's the main function. So what am I doing? I start off doing some just some argument stuff. On line 144, what I've done is I've declared an IO context. So IO context in the context of ASIO is a bit like a dispatcher. So the IO context is, if you like, kind of the active agent behind the scenes, which is actually there, picking up the asynchronous events and then dispatching them to the coroutines. That's actually what's kind of spinning around, if you like, sort of, kind of making it work. So what I'm doing next is I'm going to spawn a coroutine. So when spawn's invoked, basically what happens is Boost ASIO uses a strand to dispatch an internal handler that creates the coroutine. And in this case, I'm passing it an entry point called doListen. And then what happens is doListen gets invoked in the call to spawn. We do some setup, and then typically the coroutine will yield based on some async function call. So just before we get into doListen, I've got a vector of threads. It's very easy to kind of multi-thread the IO context, and I'm just running the IO context run function in a number of threads that I've specified on the command line. We're going to have a look at do listen. As I said, basically what we do is we just run through some setup. So those of you that are sort of familiar with kind of networking code, the open and the bind and the listen, these are all sort of fairly familiar concepts. And then basically we do some setup, and then we get down to the asynchronous accept. So what this is going to do is it's going to yield the coroutine and then to the dispatcher, and then the dispatcher will at some point in the future wake this coroutine back up once we've had a TCP connection onto the port on which we're listening. So when that happens, we get a connection come in. First thing we do is we resume on line 117. First of all, check for an error, and then we're going to spawn another coroutine. And this time, basically, this second coroutine is going to actually do the session. So we're going to actually service the user's request, and we're going to create a response, and we're going to send it out. So if we're going to have a look at do session, okay? So again, similar idea. You've got an infinite for loop, so it looks a bit like a thread body on line 40. We're going to do some setup. I'm going to pend on this async read on line 47. So that's going to effectively yield back to the dispatcher. And then at some point, I'm going to have some data that I've read is going to come in from the network. And then the coroutine will be woken up on line 48. We'll check for errors. And then we're going to go into this piece of code, which is going to basically handle the request. So by handle the request, what I'm going to do is to prepare a response and send it back to the user. Before I do that, what I'm going to do is, at this point, I'm going to print out the stack trace. So I'm going to ask for a current stack trace, and I'm going to go through each stack trace entry. So if you like, each stack frame, I'm going to print source file, source line, and I'm going to also print the description as well. I've done a little bit of formatting on the description. Does anybody can anybody tell me what's going on there? Any idea? Remember, the description string is the name of the function, its template arguments, and then a list of parameters and their template arguments as well. Any ideas what that's doing? That's right, exactly. So Roger's spot on. So it's stripping off, I'm deliberately stripping off all of the template parameters and also the parameters that are in the function as well. And the reason that I'm doing that is because if you look at the output, which is here, then immediately it becomes very complex. Now, I've done it like this, so you can sort of filter out things like, so I can look at the function calls like this, or you can look at the sequence of code like this. But actually what I'm saying is that if I was to, well, it was impossible to put the actual output on the screen. But even when you're kind of looking at it, even for a 160-line sort of fairly small program, it's extremely complex. So just be a bit mindful of that if you're using stack traces, because I think a lot of the examples tend to be quite, sort of neat and concise. But actually, if you're using it in sort of real code, then when these stack traces actually fire, they can be very complex, and you need to kind of like have factored that into your thinking a little bit. So, okay. All right. So asynchronous signal safety. So how do I get a stack trace and a signal handler? Okay, so this question comes up a lot. See it a lot on Stack Overflow. It's a very sort of obvious thing to ask the question of, I'm getting a segfault. How do I get a stack trace in that instance, in that use case? The answer is it's kind of tricky to implement safely. You've got to be very careful. The collective wisdom is basically to collect minimal information in the handler, so in the signal handler, and then resolve that outside or in another process. So what you don't want to be doing is like demangling in a signal handler or printing, sort of iterating through stack trace entries, so stack frames, and printing them out in a signal handler. Much better idea is to sort of dump that somewhere else and then process it offline or, sort of at some point when the system's in a less critical state. If you read the proposal for stack trace, it's not currently signal safe. So the authors sort of say that because it's actually, again, very difficult to do in a portable way. I totally get that. Although the design is extensible, so it could be in the future, which will be interesting. But like I said, if you want to do that sort of thing, have a look at CPP trace, and also Boost has a safe dump to function which is safe to call from signal handlers, which does exactly what I said. So collects minimal information and then dumps it outside so that you can process it later. But yeah, both CPP Trace and Boost have some really quite good advice on this. So definitely, definitely worth a look. All right, conclusions. All right, so stack traces, they are very useful. They provide a lot of enrichment, useful for introspection, and you can do object lifetime kind of debugging as well. Stack depth actually can be a very useful proxy. So if you don't need kind of all of the information that comes in a stack trace entry, and stack depth itself actually is just quite useful. It's very easy to store it. So if you're on an embedded system, for example, it's easy to chart. So give some thought to just actually looking at the stack depth. Be careful in signal handlers. As I say, don't try and call code that is not signal safe in a signal handler. And also just be mindful of the stack trace output, because it can be extensive. And as I say, if you're using this as a mechanism, I mean, one thing that I've seen happen in my company is that we've put stack traces in various parts of the code that we thought were useful. And then actually when they fire in the field, you get something that's very complex, and it's not necessarily that helpful. So, and this last point as well, I think what I'm just going to simply say is that think about how you're going to debug when you start designing the code. Because we have a sort of phrase in my company that says, the project's not over when we give the code to system test. I mean, the project is, the work is done when we've, met our commercial objectives or whatever. Yeah. So having some, so giving some thought to how we can actually debug this in the field in the design phase is actually quite useful, and it does pay dividends, to be honest. So, okay, some resources. So there's a really good CPP Weekly, and Sandor Dargo did a blog post. They quite sort of give you some kind of introductory documentation into stack trace. The Boost stack trace documentation is probably the next place to go, I would say, to have a look at. And then in terms of signal safety, there's some very good docs, again in Boost, on theoretical async signal safety. There's the signal safe tracing in CPP Trace. And also, actually, the Linux man page is actually quite useful for this. So those are the kind of the best resources that I found for stack trace as I was sort of doing my search. And that's it. So, any questions?